So talking about how to read an iron spectra is really hard to do on a board and really irked me in grad school and be like, I'll do a chalk talk. Well, this is the whole reason we have PowerPoint visual media is because your crude drawing of the boards are going to be nowhere near as good as the actual data you measured and what a computer plot is. So I'm going to try to superimpose some images on top of this video so this way you can see what I'm talking about. So when it comes to FTIR, there are two powerful uses of the technique. We're only going to utilize one of them. So let's talk about the one you're not going to utilize, and this is quantization. Because IR measures absorbance, it does follow Beer's law. And so in principle, we can quantify how much of a particular compound is in there or how much of a given functional groups we have on there if we have a set of standards. That's a much more advanced technique. Practically what we're going to do is we're going to use FTIR in order to figure out what functional groups are present in a molecule. And this is going to be complementary to the mass spec and the NMR data. See, the thing with the NMR is that there is oxygen NMR, there are halogen NMRs, but they're prohibitively expensive. So something like oxygen 18, that is the only NMR active isotope, and it costs thousands and thousands of dollars just for milligrams of it. So we typically don't do it. The IR, however, is going to measure oxygen because of oxygen's present in functional groups. So the IR here is going to give us a feel for what functional groups are present, and what we're going to look for are two characteristics of the peak. The first is the shape of the peak, the second is the position of the peak. Now, full disclosure, these 100 wave numbers, 100 inverse centimeters, that's what's referred to as the fingerprint region. So if you had a database, you could actually compare that region to known databases and say, this is the compound I have, because typically that region is unique to a given compound. But we are not going to do that for two reasons. One, we do not have access to these databases. The second and far more practical is that if you're working with an unknown, it's good to understand how this technique works. If you don't have a database to compare to, or your compound isn't in the database, not being able to analyze the rest of that spectrum puts you at a severe disadvantage. So let's talk about how you would use it. So you've got your NMR, you have an idea of probably what functional groups are present by chemical shifts, but the honest answer is that there are a lot of functional groups that have similar chemical shifts. So what you're going to do is you're going to go to the IR, and the IR is going to tell you what functional groups are present. So if we're looking for something like CH3, CH2, CH groups, there are bending frequencies associated with that based on their hybridization, and this has to go with how their dipole moment is affected by the functional group. If we have oxygen-containing compounds, something like alcohols, these are typically broad peaks, especially our carboxylic acids, and they're broad peaks because the OH groups associate with each other. If they were isolated and they weren't exchanging their OH groups, we would actually see a defined signal, but because we see the IR takes so long in terms of length scales, the OH groups get broadened out, versus something like a ketone or an aldehyde. Because those don't participate in hydrogen bonding and they're not exchanging hydrogens, they typically tend to be more narrow bands. If we want to find NH groups or amine functionalities, we'll see those in specific areas. So the complement of IR with NMR and mass spec is that it's going to give us a feel of the NMR can basically tell us what functional groups may be present, and we're going to compare that to the IR to see what functional groups are actually there, or would at least be consistent. Because the thing about the IR is that just because they share similarities in the NMR doesn't mean they share similarities in terms of the IR. Now this is also going to be true for the mass spec data as well. We're going to see fragments and we expect them to be associated with a functional group. Our IR is going to tell us that those functional groups are there. So what we should see is a mass difference, or at least a mass corresponding to whatever functional groups are being observed in the IR. So if you're seeing OH groups and alcohols in the IR, you think they're there, you should see a similar chemical peak, chemical shift in the IR and the NMR, as well as a similar fragment in the mass spec. So big picture, your FTIR here is going to give you an idea of what functional groups are present. It's going to help you tweeze out ambiguities in your NMR. It's also going to help you identify what oxygen and amine groups are present in your compound, because your carbon-13 and your 1H NMR may not be able to resolve those because things like oxygen, there's not enough isotopic abundance to see it, and with nitrogen, we typically don't run that type of NMR.